Okay, so just to repeat what we were saying, so for 5B, again, we want to go the modular approach, okay? And 5B asks you to design a tertiary full adder. A tertiary full adder circuit, and I really want you to do this as an exercise. I don't know how many of you, after going back home, actually tried to attempt to design the BCD adder all by yourself. Let me see, just raise your hand. How many actually did that? Going back, try to design the entire BCD adder from the scratch. Okay, I have 2. Because if you're not doing that, you will not be able to, get expertise on that and then move on to a new idea here, right? Because you have something, you need to get expertise on that, be confident on that approach, and then you can apply that approach to a different thing. Unless you get confident on a particular approach, you will never be able to, you'll never have the confidence to apply it on a completely new problem. So it's very important that you do it. And then, so how many of you got this problem? Let's see, tertiary full adder circuit from the class. Just raise your hand. How many of you actually you think you got this? Okay. By the modular approach, not the long way, but the modular approach where you use the adders to get it. All right. So not many. So what I'm going to do is I would extend this homework because I really want you guys to do that. All right. I'll extend this homework to be with a new due date of, let's say, Tuesday. Okay. So you'll have some more time to work on it. But the approach is you go back to my BCD adder example, do it yourself without looking from the scratch, understand each step. Yes, you'll get another attempt to submit. Understand each step, be confident in that in your understanding, then apply the concept to the to the tertiary adder. Yes, Armando.
So for like 4B, what you're saying, like combine the 4 sensors, like 2 of them, right? So what would I ground one of the inputs?
You ground one of the input, but you cannot directly combine them. See, we have 2 sensor, two of these modules, right? You have okay. You apply 4 sensor outputs to one of the module, 3 to the other module. You ground one of them, which is fine. Okay, but you have 2 outputs, F1. Let me call that F1 and F2. Ultimately, you need to have one function that determines based on the applied values of the sensors. Oh, I have 5 here. C, D, E, F, and G. Right. So what goes here? That's what you need to determine here. There's something that goes here. Do I use an OR gate? Would it work? I don't know. That's something I would like you to think logically. Does that make sense?
Yes, thank you.
All right. So I would like you to attempt, even if you have done the first approach at the gate level, I'd still like you to attempt this approach where you use these modules. I have 2 outputs. How do I combine them to get the right function? Okay. So you have more time to work on this. So think about it and work on it. Now going back to the tertiary adder, I'm not going to give you the entire solution. I'm just going to get you started on this. Okay. Now again, what is the tertiary? So since you've already done it, now again I can define my tertiary coded or binary coded tertiary number, if you go, using 2 binary bits, right? 2 binary bits to encode a single tertiary digit. Again, my tertiary digits goes as 0, 1, and 2. Right? I don't have a 3 there. It's base 3. So my digits themselves goes as 0, 1, and 2. Okay. So 0 is encoded as, so I need at least 2 binary bits to encode those digits. So 0 is encoded as 0, 0. 1 is encoded as 0, 1. 2 is encoded as 1, 0. Okay. All right. Now, if I want to make a full adder, right? Again, if I want to make an adder, like an n-digit tertiary adder, I need to make a full adder module, right? Just like what we have done for the BCD adder, which made a full adder module. So again, the level 0 diagram for that would be, that's the tertiary full adder. Again, that's one tertiary digit, which is encoded as 2 binary bits. That's the second tertiary digit, encoded as 2 binary bits. Then I have the C in, right? So I'm going to call that A1, A0, B1, B0, C in. And how many outputs do I have? For this level 0 diagram, I have 3, right? So I have C out, then S1 and S0. Can I do this using the K-map approach? Yes. I mean, I have 5 inputs, so I'm looking at a 32 cell K-map. It's doable. It's long, as you have complained, and I would not go that route because it's long. It's just too tedious. I want to write down a 32 cell K-map, 32 a truth table consisting of 32 entries. Not very fun to do that. However, can I do it the alternate approach like we have done for the BCD adder? Now again, when I'm doing the addition operation, all I'm doing is, what am I doing here? I'm adding this with this, right, along with the previous bit, of course, but I'm adding this number with this number. Again, this number is a binary, 2-bit binary number. Of course, it's an actually tertiary number, but it's still encoded as a 2-bit binary number. That's a 2-bit binary number. If I want to add them together, can I get by instead of designing it from the scratch, can I use a 2-bit adder, a binary adder, to perform this addition? Because if that's the case, then I don't have to do anything there. I can just use the 2-bit binary adder, apply these inputs along with this to the 2-bit binary adder, and I get the answer. So what you need to check then is, will I be getting the answer, a tertiary answer all the time? Will I be getting a consistent tertiary formatted answer all the time, right? For example, so I have a 2-bit adder, okay? I have C in, where that C in goes. Then I'm applying A1, or A1, A0, B1, B0. Out comes my C out. That's sum, S1, S0. That's a binary adder, okay? And we know exactly how to design a binary adder. I don't have to, and you don't really have to show the inner workings of the binary adder. You can just show in your working thing. You can just show that as a block and say that that's a binary adder, which is fine. I will accept that because I know you know how to design a binary adder. I don't expect you to show the inner circuits in that block. Okay. All right. Now I will test few conditions. For example, 2-bit adder is the same as half adder. Not necessarily right. 2-bit adder is not necessarily the same as the half adder. Okay, so that's a 2-bit binary adder. Okay, and remember, I am getting a CN. It does have a CN. It's accounting for CN, so it's still a full adder. So it's a 2-bit full adder. Okay. All right. So I will add them. Let's say 1 plus 1. In tertiary, I get 2. That corresponds. If I convert that to a binary code, that will be 0, 1, getting added to 0, 1, and that is 2. Is that in the right tertiary format? It's in the right tertiary format, right? That's giving me a number 2. Tertiary number 2, that's 2. That's fine. What about 1 plus 2? I get a 3. When I convert that to tertiary, that corresponds to 0, 1 being added to 1, 0. And I get 1, 1. That is binary 3. But is it in the right format? Is it in the right tertiary format? What would be the right tertiary if I want to represent that? Of, sorry, because everything is in tertiary. This is tertiary addition, tertiary. So the right sum here would be 1 0, right? 1 0, absolutely right. So here, the right tertiary format would have been 1 0 0. But I'm getting this. So obviously, sometimes it works. Sometimes it doesn't work. I need to do some adjustment here to make it work. Exactly going back to the decimal error. Okay. I think that's sufficient clue. I hope now you should be able to take it from here. Does that help? Because I don't want to give out everything and then the fun is lost. Yeah. The joy of getting the problem. So I hope with this clue, you'll be able to move forward and actually, and you will see that this is much more simpler than the BCD error. Much more simpler. Okay, because we are just dealing with few number of, in the BCD error, we had to still, even to develop that control logic, we had to look at the five input K-map. Right here, that's not the case. You would still be needing a 3-input K-map for this. So it's much more simpler. And you would, if you get it, you'll be able to do it within 2 or within 5 minutes. So much more elegant, short solution. All right. Any other questions here? Concerns? Okay, if not, let's move on. So I hope you'll use the time. So this will be due on Tuesday. So you'll have the weekend and Monday to work on it, okay? Hope that's plenty of time now. Because I really want you guys to get it. And that's one reason. The other reason is because I will be having a similar kind of a problem on the midterm. So I want you to get that midterm problem as well. I want you to be experts on this. My goal is again to introduce you to some design problems, okay, or design approaches that you can apply not just for this class but moving forward as well. Okay. All right. So that's my motivation. That's why I'm pushing you so hard. All right. So just to give you a quick recap of what we have done in the last class, or towards the end of the last class, we discussed about the concept of flags. Okay. Flags. And these flags are very critical. This actually allows you for decision making when you're programming. And we have seen various instances where you want to make the decision, right? For example, you want to run loops. Most of the time when you're writing the program, most of the time we are basically running loops of different kinds. We are doing if-else statements, while statements, for loops. And in each of these programs, we are looking for a condition. We're checking for a condition. That's the common thing that kind of encapsulates what we're doing behind those codes, checking for conditions. Right. So when you write the program, what is happening at the corresponding hardware, at the hardware level. So what I would like to show you now is the classification of this computing of the languages. Okay. In your 356 class, you should be able, most likely you'll be taught a little bit, at least introduced to the concept of assembly language. Okay. So broadly, you can classify the programming languages into 3 types. Okay. So you have what is called high-level language. Most likely you must have learned that in some degree before. Like, for example, when you're talking about C++, Java, C, these are all high-level languages where you have a syntax, where it appears more like English statements, right? So reading the code, you will exactly know what that code is supposed to be doing. And then you have what is called the middle level language, which we call, or in other words, the assembly language code, okay, and which consists of mnemonics, basically very short segments of code that you would use, like which is still descriptive. Okay, just to give you an example, wait a minute. Just to give you an example here, a mnemonic could consist of a statement, single statement like a add a comma b. Okay, that's a statement. That's a programming statement. Okay, and then at the lowest level, so that's mid level. Okay, that's one step above what is the lowest level. Okay, and at the lowest level you have what is called the machine language. Now this is the machine language that's directly understandable by the microprocessor or the microcontroller that you're trying to program. Right, and of course, as you can guess, the machine language would basically consist of ones and zeros, because that's exactly what is understood by the machine, ones and zeros, right? So assembly language is one step above that. Okay, so each code, each mnemonic, for example, like this, has a particular machine code associated with that, and you would need a compiler to basically convert that into that particular machine code. Okay, and high level languages at a very high level, uh, and oftentimes when you write a high level language, you have a lot of redundant code that goes into when it's compiled into the machine code. So if you want to really design, or if you want to program these embedded systems with very compact programs, then this assembly language code would be the best way to move forward. Okay, and here is an example of the mnemonics. It's very descriptive still, but the way you think about writing a program is slightly different than how you would do uh, for high level language. For high level language program, you really don't need to understand too much about the hardware architecture, right? Like the computer architecture or the hardware, exactly how the memory is located, what you have inside the arithmetic logic unit, how are the registers located, and what are the registers called, and so on and so forth. You don't really need that knowledge when you're writing high level language code. However, when you're writing the assembly language, you need to have some kind of basic idea about the hardware configuration, hardware architecture of the microcontroller. Okay. So for example, here are some of the examples. Your code may include instructions such as ABA. Again, what does that mean? That basically adds a B. Basically, you can think about B and A here as two temporary memory locations that are present within the um, within the microcontroller. Okay, and so you're adding the contents of A with the contents of B, and the contents of, and the addition product, or the addition or the sum, is being stored back in the register A. Okay, in the temporary memory location A. Okay, and let's not worry about the addressing mode at this time. Hopefully you'll learn about that in the next version of this class. But you can see that this particular instruction ABA is encoded as a binary code. Of course, here that binary encoding is shown in hexadecimal. Again, if you know, because that's you can see that 1, 2, 3, 4, right? That's 16-bit binary code, and your hexadecimal. The good thing about working with hexadecimal numbers is that it encodes binary numbers in a much more compact fashion, right? So that's a 1806 is the actual machine code that will be written in the program memory of your microcontroller. Okay, so 1806, that means in binary that would read as 0001, 1000, 0000, and then 0110. So that's the binary code corresponding to this program or this instruction that will be stored in the program memory. Okay, all right, and then you have other instructions as well. So your codes, and we'll actually take an example toward the end of the class, or maybe in the next class, of a simple assembly language code. How does that actually look? It's a lot of fun actually working and programming in assembly language, because it's a different way of thinking to program. Okay, all right. And you will notice that you also have in this particular table. So again, this table is obtained from the Motorola instruction set. That's the HCS12 microcontrollers. Okay, that's the instruction set for that particular microcontroller. And then in here, what you have is some other again a temporary memory location called the conditional code register, and this makes much more sense when we talk about flags, and we will revisit that particular aspect, that particular column, once we actually wrap up our discussion on flags. Okay, all right. So I just wanted to show this. All right, let's do that. And oops. And I wanted to also show this. This is again the instruction set, which shows the compare operations. So CMPA is again a code. It's basically a assembly language code, a mnemonic. We call that a mnemonic. Compare. A is the temporary location that is present, temporary register or memory location that is present within the CPU. And you're trying to, in this particular operation, you're trying to compare the contents of A with the content of the memory location that you provided. Okay. So when I'm trying to compare anything like this at the hardware level, as you can see, it basically performs this subtraction operation. Okay. It's subtraction operation and looks at the result of the operation. Okay. So that's the key. Whenever I'm doing anything for condition checking, when I'm trying to compare two numbers for condition checking, at the hardware level, this is what happens. The subtraction operation is what happens at the hardware level, and then it does the comparison operation. How exactly does it do the comparison operation? That's the focus of our class today. Okay. And as you may have guessed, that's basically done through the use of flags. Flags are the ones that allow you to do that. So again, what are flags? These are 1-bit status indicators, if you will. Okay. So that indicates the result of a particular operation. Okay. All right. So let's do that. Let's look at a simple code. Okay. Let's say I'm trying to write this in the higher level language at this time, so that makes a little bit more sense to you. Let's say if I'm writing a code something like this: if A is equal to B, I perform certain set of operations. So that's the code I write at the high level language. Okay. And at the hardware level, at the most fundamental level, what is happening at the hardware? Again, as we discussed in the last class, we want to use flags instead of looking at the entire answer and looking to see if each of the bits is 0, because again, as you may have guessed, at the hardware level we are performing a minus b operation, and we're checking if a minus b operation gives you a 0, right? Because if that's 0, that means a is equal to b, and those instructions are executed. Okay. Now, if I don't have a flag, then I have to make sure that, let's say A is a 16-bit number, B is a 16-bit number. Okay, because right now we are using 16-bit computers, right, or 32-bit computers. Then I have to basically look at 16 zeros to make sure that each bit is a 0, right? Which is not very efficient solution. Can I configure a flag, a single bit flag, a single bit, a single bit that just tells me that yes, if I obtain all zeros, then the flag, which in this case let me call that the 0 flag, will be set. And if I have at least one, even if I have one in that number, then my 0 flag will not be set because that's not a 0. Then that will be 0. So 0 flag will be set when a minus b operation results in a 0. It will be not set for any other number, any other sum. Okay. How do I design this? So let's get back to the adder/subtractor circuit now. Okay. And your next homework, which is a required homework, that means you have to do it, otherwise you'll not get a credit for that, will be on simulations. So you'll be actually simulating this adder slash subtractor circuit along with the flags that we're going to discuss today. Okay, and B2Spice is one suggested program, but you can use other programs like Multisim is another program that can be used to simulate these kind of circuits. B2Spice, there's a light version that you can use, but the university has a full version. I would recommend that you use the full version so that you can actually do it in a modular way. So you can create the simple circuits and convert that into a block, into a module, and you can use them as modules to build larger circuits. Okay, so let me go back to the full adder circuit, full adder slash subtractor circuit. Okay, let's say that's an 8-bit full adder. Okay, that means I'm applying A 0 to 7, right? 8 bits. That means I have 8 inputs going in, that is shown with a single arrow. Then I'm applying my B's 0 to 7 through each individual B is of course applied through an XOR gate, as you can see, and that's your control input that specifies, that's my CN, that specifies how you're configuring your circuit, whether it's an adder or subtractor. So we have seen this already. Okay. That's your Cout. Okay, and that's your S7, S6, S5, S4, S3, S2, S1, S0. So that's your 7 bit sum. Okay, all right. And I want to design what is called a Zflag. How would I do this? A Zflag that says that is set if S7 through S0 are all zeros, is equal to 0 otherwise. Now I would like you guys to think and come up with a simple solution by which I can obtain the Zflag to this circuit. Can you think about something that we could use so that I can have a single bit indicator that indicates, that is set when all of those inputs are zeros, that is not set, or that is reset otherwise. Think about it. I'll give you, let's say, a few seconds. What can I do here? Can you think of a solution? Eric? I have two Erics here. Eric, let's say Eric Dolan. Do you suggest a solution here for a Zflag? I have 8 bits here. Somehow I want it to, okay, a NOR gate. So basically I will pass all of them through an OR gate and see if that works. That's an OR gate. Again, going back to so I check the truth table for an OR gate. Let's say I have A and B and F, 0, 0, 0, 1, 1, 0, 1, 1. For an OR gate, if I have one, if one of the input is a 1, then the output is 1, right? So the NOR gate would be the opposite or the complement of that. So in this case, these are all zeros, and I have 1 only for this case. In other words, my NOR gate is set only when each of these inputs or each of these bits are zeros, right? So that gives me my Zflag. That's exactly how I want my Zflag to work. That's my Zflag. So I don't have to look at individual bits. I can just simply look at the Zflag, A minus B operation, check at the Zflag, look for the Zflag, and if the Zflag is set, then I conclude that A is equal to B. Okay. All right. Now, before we move on for the other flags, I would like you to ponder about a few things. And these are some of the questions that you should have asked me, right? Now, when we designed this full adder, this piece of hardware that can perform addition operations, the first question that you need to ask me is, can it only do unsigned addition operations? Because your data can come as unsigned numbers as well as signed numbers, right? You have two possibilities here for the data. We have designed this, but can it do, so what can it do? Can it work on unsigned numbers only, or can it work on only signed numbers, or can it work on both numbers? What do you think? This piece of hardware, can it work for how can we apply this? David? It should work because we designed it for the 2's complement. So your answer is, okay, it works for both numbers, so unsigned as well as signed. Okay. So that the follow-up question would be, how do I distinguish between them? Right? I have two. Let's say, for again, another way of putting this is, I'm writing a code. Okay. Let's say if A is larger than B, then do certain operations. In this case, I'm actually testing the magnitude between these two numbers. Again, as I mentioned before, at the hardware level, what is happening? The hardware level, again, every time I'm checking for a condition like this, first of all, I'm doing this A minus B operation. Right? I do an A minus B operation, I'm checking for the result of that operation. Now, but the challenge here is, again, the challenge, let's say I'm working with unsigned numbers. As a programmer, I know I'm working with unsigned numbers, right? Remember that the hardware itself wouldn't know. It does not have a mind of its own. Okay, so somehow I have to convey that information to the hardware as a programmer. So all the intelligence still lies at the programmer. So let's say I'm working with unsigned numbers. I know as a programmer that I'm working with unsigned numbers. Let's say A is 0, 1, 0, 1. B is 1, 1, 0, 1. Okay. When I'm doing this operation A greater than B, in this case, it's obvious. In this case, my B is larger than A, right? Because I'm working with unsigned numbers, obviously this has a larger magnitude than this number, right? But what about if I'm working with, so again, I do this A minus B operation, look at I'll probably design some flags and then look at the flags. Now, what about if I'm working with signed numbers? But remember, for the hardware itself, it's just bits 0, 1, 0, 1, 1, 1, 0, 1. They're applied to the hardware. It just does its thing without really thinking. There's no mind there. It just does its thing because we are the one who designed the hardware. Then you have the signed number. Let's say in the next instance, I'm working with signed numbers. Let's say my A is again 0, 1, 0, 1. B is 1, 0, 1, 1. When I'm working with signed numbers, of course, my A is larger than B. In this case, because my A is positive, B is negative because I have a 1 in the most significant bit position. B is negative, A is larger than B here. Now, how can we convey that information though? Because for the hardware, it's just that. It's just bits. right? So that's the next question that we need to ask ourselves. How can it distinguish between, if the programmer is trying to work with signed numbers, or if the programmer is trying to work with unsigned numbers? Okay. It turns out that it's the flags. The flags come to our rescue here. The flags are the ones that enable us to do that distinction. Okay. All right. So let's consider for the first case unsigned numbers. Okay. Unsigned operations for now. Let's try to design Cflag, right? So that's your Zflag. So we got that we need that Zflag. So let's focus on unsigned operations for now. So these are unsigned operations. So that means my A and B are unsigned. And what I want to do is I want to come up with a set of flags. Set of flags that can perform these operations, that can perform these conditional checkings. A larger than B, A less than or equal to B, A larger than or equal to B, A less than B. When I say A larger than B, that means A should be strictly larger than B. Okay. When I say A larger than or equal to B, that means A can be larger or equal to B. Both of them, that is fine. If that condition is satisfied, then you execute that set of instructions. Okay. So these are the conditions I would like to check. We have already come up with the answer for how to check for this condition, right? A equal to B. You perform A minus B operation. Check for the Z flag. Right. So this is done. We want to do the rest of these. All right. So let's see how we can do that. Again, for each of these conditional checking, I am performing this operation at the hardware A minus B operation. In this case, A minus B, A and B are confined to be unsigned. Okay. So we are looking at A and B as unsigned numbers. Now, what I would like you to think about is, can I come up with a flag? How do I check for that, for those conditions? What would be an appropriate flag that would allow me to do that? Any ideas here? So we need to go back to our 2's complement subtraction operations. Okay. When we did this, of course, at the hardware level, we are really doing A plus 2's complement of B, right? A plus 2's complement of B. And two possibilities can happen here. Two possibilities. When I'm doing this particular operation, I can have a C out. C out becomes 1, right? Or C out can be 0. Right? When you're adding A to the 2's complement of B, the C out, just like, for example, second example, maybe that will clarify. Again, let's look at a simple example. Let's say A is 0, 1, 0, 1. B is 0, 0, 1, 1. Okay. Of course, A is larger than B here because, again, these are both unsigned numbers, both positive numbers. So if I want to do A minus B operation, that corresponds to taking 0, 1, 0, 1 and adding to that the 2's complement of B, which is 1, 0, 1, 1. Right? I add them. 1 plus 1 is 0, 1, 1. 1 plus 1 is 0. Again, A here is 5, B is 3, 5 minus 3 is 2, 5 minus 3 is 2. And remember what we did for the end carry. This is the end. This is called the end carry. We basically ignore that. That's my result, right? So when A is larger than B, when I perform A minus B operation using the 2's complement approach, I produce an end carry. And we have proven this, right? On the other hand, if my A is 0, 1, 0, 1, B is 1, 1, 0, 1, obviously my B is larger than A. So A minus B here corresponds to taking A 0, 1, 0, 1, adding to that the 2's complement of B, which is 1, 1, 0, 0. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. That's 1. So that's 8. I'm sorry, that's not 8. Let's not worry about this. These are unsigned numbers. Okay. So let's not worry about this. And my C out here is 0. So you can already see I'm getting a clue here. When A is larger than B, I produce C out. When A is less than B, I do not produce a C out. That means I can potentially use C out itself when I'm trying to compare unsigned numbers. I can potentially use C out itself as a flag, right? A flag, a single bit indicator that can indicate to me which number is larger than which number. All right. So I can use C out itself as a flag. But again, that will not tell me for all of these conditions. I still have to do something else, something more to that. Okay, some combination of flags there. That's one thing. You can also look at this alternatively. You can also look at this way. Okay. Let's say A is 7, B is 3. Okay. Yeah. A is 7, B is 8, let's say. I'm doing A minus B operation, which basically says A 7, I'm subtracting 8 from 7. Can I do this? Obviously, 7 is less than 8. That means if I had another digit here, 3, for example, if I had another digit, I would have borrowed from this digit, right? I would have borrowed 1 from this digit. In this particular example, I don't have that luxury. So you can consider that if I want to do this operation, that means I need to borrow from this imaginary borrow. Let me call that imaginary borrow position. Okay. If I want to perform this operation, that means I need to borrow from this imaginary borrow position. Whenever I have to do that, that means my borrow flag is set. Borrow flag is set. That indicates me that yes, I have to borrow from an imaginary borrow. Of course, if my A is 8 and B is 7, 8 minus 7, I don't have to borrow from an imaginary borrow here because I can subtract it directly. In this case, my borrow flag is not set. Okay. Are you with me until this point? There are two different ways of thinking about this. One is when I'm doing the 2's complement approach, my C out that comes out, right? My C, if I can look at the C out. If my C out is a 1, that indicates that my A is larger than B. Okay, let me summarize this here. I can look at Cout. I'm doing A minus B operation. Look at Cout. Call that borrow flag. Okay. Cout. I'm doing the A minus B operation. When A is larger than B, my Cout is a 1. What about my borrow flag? If A is larger than B, I don't have to borrow. My borrow flag should be 0. If A is less than B, my Cout is 0. But for my borrow flag, I have to borrow from the imaginary borrow position. My borrow flag is a 1. So the relationship between the borrow flag and my Cout, as you can see here, my B flag, borrow flag, is basically Cout inverse, right? Is the inverted version of Cout. That's the relationship. And traditionally, we use B flag to look for the condition. For A larger than B or A less than B, I look at this B flag. So I need to construct a B flag. So how do I construct the B flag here? I invert Cout. And that will give me the B flag when I'm doing the subtraction operation. When I'm doing the subtraction operation, that means when my control input is 1, I'm doing the subtraction operation. Then to get the B flag, then I need to basically invert my Cout, and I get the B flag. Okay. Are you with me until this point? Does that make sense? Any questions? Let me just take a pause here. Let me see if you have any questions about anything discussed so far. Okay, no questions? Jacob, you're all good? Okay, I hope you're there listening. But anyway, so that's the relationship. So I'm trying to come up with a flag that can indicate for unsigned operations the relative magnitude between two numbers. Okay, so that B flag is Cout prime. Okay. Now, there's another condition I would like to check before I finalize this. I'd like to check for another condition. Typically, let's say I'm still working in the still working with unsigned numbers. Okay, I'd also like to check for overflow condition. Overflow. As we discussed before, right? When I'm working with binary, when I'm working with these digital systems, I'm limited in size. How many bits my memory location can hold, right? If I'm working with 16-bit memory, that means each memory location can hold 16 bits. That's it. So my numbers can be 16-bit long, not larger than that. When I'm trying to add two 16-bit numbers together, my number can exceed 16 bits sometimes, right? And in which case that results in what is called an overflow condition. And I need to have a mechanism by which I should be able to check for the overflow condition. Okay, so overflow condition checking. Now for unsigned numbers, what can I use for unsigned operations? How do I check for overflow? Let's say, just to simplify, let's say I'm trying to add two numbers together. What can I use to check for an overflow condition? Any ideas here? Cout, very good. Cout, right? When my sum exceeds, in this case, 8 bits, then the accurate sum is represented in 9 bits. The 9th bit is the cout. So I can use my cout as an overflow condition check, right? So when I'm doing the addition operation, my control input is 0 here, but then let me call that Cflag, cout Cflag. So your Cflag should borrow flag is nothing but the Cflag. The Cflag, so okay, let me put it this way. Your borrow flag B flag equal to Cflag for subtractions. Okay. Now I would like to use my cout as the indicator for my overflow condition. Okay. And what do I do here? I would like to use my Cflag. So whatever this fleece is basically about, I would like to use my Cflag to check for overflow condition, overflow, as well as to check for the B flag condition for both purposes. So when I'm subtracting two numbers, I can check my C flag. If a C flag is set, then my A is less than B, right? A is less than B, my C flag is set. A is larger than B, my C flag should not be set. When I'm doing the addition operation, my C flag is set when I have an overflow condition, and not set when I don't have an overflow condition. I want to use it for both purposes. Does it work for both purposes here? So that's for that. Let me summarize what I'm trying to say here so there's no confusion. So that's for the conditional checking, and that's for the overflow condition checking. Overflow condition, A plus B, C flag. If A plus B results in an overflow, I would like my C flag to be set. No overflow, I would like my C flag to be reset. Okay. All right. But the problem is, if I invert this here, when I'm doing the addition operation where my control is 0, I'm inverting my C flag as well all the time, right? So I need to be able to invert C flag only when I'm doing the subtraction operation, and not invert C flag when I'm doing the addition operation. How do I do this? If you notice, this and this is happening when I'm doing a subtraction operation. My C flag should be set when A is less than B. C flag should be reset when A is control logic and XOR gate. Perfect. Yes, that's very good. So you got that, right? In other words, if I want to get the right C flag that works for both of these conditions, what I should be doing is I use an XOR gate here that gives your C flag, where the other input to the XOR gate would be your control input. So now that will give me my C flag. Okay, so when I'm doing the subtraction operation, then my C flag is the inverted version of cout. Every time I have to borrow, my borrow flag is my C flag acts like the borrow flag. Borrow flag is set. Consistent now with this. When I'm doing the addition operation, and when I want to look for overflow, then my C flag, my control is 0, and my C flag is not inverted. So every time I have an overflow and I'm doing the addition operation, my Cflag is set, no overflow, Cflag is 0. Of course, the overflow condition also works for subtraction operations as well, right? Because I have this, here's a situation where you have an overflow. Because when you're working with unsigned numbers, you don't have a negative number, right? So I'm doing a subtraction operation here. I have an overflow that I should be able to detect, right? And here my Cflag is inverted. That means my Cflag is 1. That also indicates that I have an overflow condition here. So it works both ways. So that's my Cflag. That's how I would get my Cflag. Does it make sense why we have done the XOR gate operation there? Because I want to stick with the convention. For example, your microcontrollers define Cflag in this way. So I need to be consistent with what your actual microcontroller is doing, right? I could have left it at C out, but that's not how it's done actually. All right, any questions here? Does it make sense? Kamrin, is that clear? Okay. All right. So that's how I get my Cflag. Subtractions, Cflag is my borrow flag. And also I can use my Cflag as the overflow flag as well. Okay, now what we're going to do is, now that we have realized the Cflag, now I should be able to check for other conditions, right? Ultimately we need to check for A strictly larger than B, A larger than or equal to B, A less than B, A less than or equal to B. I need to check for these conditions. How do we check for those? Let's do that now. Okay, so let me write this table now. Okay, and that table will allow us to actually do this. So I have Cflag, Zflag, and let me make it a little bit smaller here. Cflag, Zflag, A minus B. Okay. Let's look at all possible combinations between these two flags. Now, if my Cflag is 0, that means I'm not borrowing, because again, when I'm doing the A minus B operation, my Cflag acts like the borrow flag, right? The imaginary borrow flag. I'm not taking anything from the imaginary borrow. That's good. My Zflag is 0. That means A minus B is not 0. What can you say about the magnitude between A and B? I don't have to borrow. The answer is not 0. That means my A here is larger than B, strictly larger than B. Right? What about if my Cflag is 0, my Zflag is a 1, Cflag is 0, Zflag is a 1, then in this case my A, of course my Zflag is set, that means my A is equal to B. Here my Cflag is set, Zflag is 0, that means A is not equal to B, and A is less than B because when I'm doing the subtraction operation, my Cflag acts like the borrow flag, and A is less than B in this case, because I have to borrow from the imaginary borrow for me to be able to do that operation. So A is less than B. Cflag is a 1, Zflag is also 1, And you will see that that does not happen. You cannot have both Cflag and Zflag 1 at the same time. All right, so with this table, what I want to do is, I want to check for this condition, A strictly larger than B. That means if I want to check for A strictly larger than B, that means I need to make sure that my Z flag is not 0, is not 1, right? A is strictly larger than B, that means my C flag, we'll just look at this expression, plus Z flag equal to 0. If I check for this condition, forcing it to be 0, then A is strictly larger than B. Let's see if that makes sense. When I have this expression, that means I'm forcing my Z flag to be a 0, because otherwise this expression is not satisfied, right? My C flag can be a 0, my C flag can be 0, but my Z flag may be 1. But by looking at this composite condition, C flag plus Z flag, I'm forcing my Z flag to be a 0 for that condition to satisfy, so that my A is strictly larger than B condition is satisfied. Okay. So that's for A strictly larger than B. And then you have, okay, that's good. Now what about A larger than or equal to B? What condition should I check for this case? A larger than or equal to B. What combination of flags should I be checking for that condition in this case? In this case, my C flag can be a 0. My Z flag can be my Z flag can be a 1. I don't have to worry about Z flag being a 1. So in this case, my condition to check for is a C flag equal to 0. Right? C flag equal to 0. I don't have to worry about Z flag now. That can be a 1, in which case this condition is satisfied, A equal to B. If this is satisfied, then A is larger than B is satisfied. So that's good. So that's fine. All right. So I'm done with the A larger than B condition, A larger than or equal to B condition. What about A less than B? A strictly less than B. For A strictly less than B, I can simply from here, since my C flag and Z flag are cannot both be 1s at the same time, I can basically have this condition C flag should be a 1. Right? Because if a C flag is 1, then Z flag cannot be a 1. And finally, for A less than or equal to B, what should I be checking for A less than or equal to B? C plus Z is 1. Perfect. My C flag or Z flag should be a 1. Right? My C flag or Z, because in this case, if this is 1, then A is less than B side condition is satisfied. If that is 1, this condition is still satisfied, and either way, my A is less than or equal to B condition is satisfied. Yes, for A equal to B condition, then I have to just look for Z flag. For A equal to B, yeah, that's correct. All right, so that's it. So for unsigned numbers, we have looked at all possible combinations of conditions to be checked. So you're done. That's good. Any questions on this before we move on for the next part, where we want to check for condition for signed numbers, which is a little bit more involved than this. Here it was a little bit more straightforward because we just use C out. and then we modify the cout to make it Cflag to follow the convention, and we are done. Any questions on this so far? Does that make sense? Again, remember that you will be simulating this entire circuit, okay, an 8-bit full adder, along with the flags, the various flags, okay, and you'll be passing different numbers through this, through different 8-bit numbers through them, checking to see if that actually makes sense, if your circuit is performing the right way. Okay. All right. No questions? Are you all good so far? Okay. So next, let's move on now to the signed number checking. Now that you know how to build these flags, I would like you to think about what additional flags should we be needing for checking signed numbers, the conditional checking for signed numbers. What additional flags should we be needing? How do I check for signed numbers now? We want to check for the same conditions. The only difference is my A and B are signed now. I want to check for A larger than B, larger than or equal to B, A less than B, A less than or equal to B. A equal to B condition is still trivial. I would still be looking at the Z flag, whether A and B are signed or unsigned. I would still be looking at the Z flag. Yeah, we need a flag to check the value of the MSB. Very good. Why? Because we are working with signed numbers, and the sign information is important, right? The sign information which is contained in the most significant bit position. That's important. Okay. So that means I can create another flag called the sign flag. Let me call that the sign flag, designated as N. Call that the sign flag. So my N is 0 implies that my sum is positive, right? Positive. Because that's the most significant bit position that indicate the sign. 1 implies sum is negative. So yes, very good. So N flag would be important. Now let's see if that N flag is good enough for us. Okay. Let's say, for example, my A, again, let's deal with 4-bit numbers to make it simple. You can always extend it to 8-bit numbers. Let's say my A is 6 and B is 8, let's say. A minus B operation should be less than 0 in this case. I'm sorry, no. These are signed numbers. So this is not 8, this is negative 8. So A is that. Let's not take 8, negative 8. Let's take another number. That's equal to plus 6. Let's take 6 and 7 maybe. Okay, 6 and 7. So 6 minus 7 should be negative 1. That means I can look at the negative sign now and make a decision if A is less than B or A is larger than B. And let's see what happens here. 0, 1, 1, 0. Adding that to 1, 0, 0, 1. I get 1, 1, 1, 1. My most significant bit here is a 1. That indicates that whatever answer I got here is a negative answer. So good. Looks like our N flag works. I can be able to use my N flag to do this operation, to check for the condition. If A is larger than B, or A is less than B. Okay. Would that be all? Is N flag good enough? Let's see. So that's what we will do is, in the next class, we will look at other possibilities and see if we can get by with just the N flag, or if we need additional flags to be able to do this conditional checking. Okay. With that, let's stop here, and let me see if you have any questions before we conclude the class. Does that make sense, what we're doing? Okay, so if you don't have any other questions, then let's conclude here, and I will see you guys next week. Okay, have a good weekend. So S7 is one of the last C out, right? S7, no, the S7 is the sum. That is my C out. S7 is the sum. Okay? Yeah, thank you. All right, thank you guys.